All right, everybody. So I am going to do something a little bit different for this unit. There is a PowerPoint presentation on tracks that kind of goes through all the nuances of this chapter. But instead of just going through that and basically going through the PowerPoint step by step, I decided I would give you guys some highlights about the real important stuff in this section. Now, this particular unit deals with some pretty heavy tools that are used in chemistry to identify compounds, in particular nuclear magnetic resonance. There is a little section at the end on mass spectroscopy, but both of these fields are really almost subjects in of themselves now. Their entire course is devoted to these topics. So I am not going to get a lot into the theory as to, how this occurs. I will explain a little bit about, obviously which atoms exhibit it, but really I want to talk about the utility of how it relates to identifying structure. And that's the main takeaway that you're going to need for this course. So let me start off by talking about NMR. So that stands for nuclear magnetic resonance. And what this essentially is a sample is placed into a machine that is essentially hit with a low energy pulse. And I'm talking radio wave frequencies here. So very, very large wavelengths, very low energies. But in order to exhibit this phenomenon, an atom must be able to interact with the electromagnetic field that's generated from hitting that pulse. And not every single atom exhibits this. There are a few that do, and the ones in particular that we're going to be looking at are proton NMR, which is by far the most useful technique, as H1 is the most common isotope of hydrogen. And so you can get a good NMR for a typical compound in less than a minute, okay? And usually you only need about 10 to 15 scans from the machine, so it's very fast to do. Carbon-13 is another isotope that will exhibit the NMR effect, but because carbon-13 is only about 1.1% carbon, you need a lot more scans, like 5,000 plus, and this can take anywhere from 1 to 6 hours in order to get a good spectra. So what we're going to talk about first is we're going to be primarily focused on proton NMR, and I'm going to go through the things that I think are the most important that you need to be able to do. So the first thing that you need to be able to do is to be able to count the number of signals, okay, that you're going to see in a given sample. So what I like to do usually is look at the compound and predict how many signals I'm going to see in the spectra. It turns out that the signals are entirely based on the symmetry of the compound. And I'm going to get into this in a separate page in just a minute. But essentially, anything that is symmetrical, hydrogens that are attached to the same carbon atom, or hydrogens that are, basically symmetrical with another carbon atom, the machine treats these essentially as the same signal. Now, there are some exceptions to this, especially when you start throwing in stereo centers, but this is true for 95% of the cases. Now, the other thing to be aware of is where these signals are in the NMR. So the location is very important because it tells you about the chemical environment that that hydrogen is in. It turns out that the more shielded or the more electron density that's around that hydrogen, the more energy that the machine has to exhibit, or basically the greater the force, okay, that the machine has to apply, the greater the magnetic field strength. So that means that those signals tend to be what we say further upfield, and hydrogens that are next to atoms that are electronegative or attached to carbon atoms that are attached to electronegative elements like nitrogen or oxygen, well, then that causes those signals to be de-shielded and it doesn't take as much energy, and those signals are said to be downfield. And I'm going to show what that looks like in just a minute, but I just wanted to introduce those words now. The other thing of note is what the signals look like. Not everything is just a single peak. In proton NMR, one of the very useful things that you'll see is that there's a splitting pattern that's associated with the signals based on how far away another hydrogen is from a hydrogen that's exhibiting a signal. And so this helps tell you about the connectivity of the compound. Now, I know, again, this all sounds like gobbledygook, but it will make sense in just a minute when we start putting it all together. And the last thing is what's called the integration of the signals. This essentially tells you the lowest whole number ratio of hydrogen atoms in a given compound. Okay, so those are going to be the four things that we're going to emphasize here. And I'm going to start off with the number of signals that we typically see in a compound. Now, the most important thing to note here is the symmetry. Okay, so first of all, hydrogens attached to the same carbon. Hydrogens attached to the same carbon are generally viewed as one signal by the machine. Okay. So for instance, if you had a molecule of methane, CH4, that would be one peak. You would only see one signal, one peak in the proton NMR for that compound. Because all four of these hydrogen atoms, the machine views as equivalent, okay? And so they all show up basically as just one signal, okay? Now, this is also true even if they're attached to different carbon atoms, as long as there is a plane of symmetry there. So for instance, if we were to look at ethane, okay, even though there are 6 atoms here, because there's a plane of symmetry right here in the molecule, the machine thinks all of these hydrogens are equivalent, okay? And so all hydrogens are equivalent. So only one peak. Okay. Now, if we go out to the next largest hydrocarbon, which is propane, all right, I'm going to pencil in these 3 hydrogen atoms here and these 3 hydrogen atoms in here. The machine is going to treat those sets of hydrogen atoms as essentially one signal. So all 6 of those hydrogens that are penciled in red, the machine will view as one signal. However, the 2 hydrogen atoms that are right here on this carbon atom, that is going to be viewed as one signal also. So you're going to have 2 signals that you would see in the proton NMR. Okay, so this would show up as a signal, and this would show up as a signal. So 2 signals. All right. Now, what about butane? Okay, so what do you guys think there? Okay, well, again, plane of symmetry in the molecule right here. These 3 hydrogens and these 3 hydrogens here and here, those are all going to show up as one signal. And all of these hydrogens here that I've colored in blue are going to show up as one signal. So 2 signals in the proton NMR. Okay. So if you're used to looking for planes of symmetry in compounds, you're going to see that a whole lot, okay, in this section. Now, it doesn't mean that you can't get a very complicated NMR, because some compounds don't really have any symmetry associated with them at all, or very little, I would say. So let's try another example here. So let's just say that we had, let's say we had a double bond here. Okay. And so let's say you were trying to figure out, well, this compound. Well, here, you know, basically both sides of the double bond are very different. You have this 2-carbon group and this 1-carbon group for this trans compound. So if you pencil in all the hydrogens, you've got 3 hydrogens here. So this is going to show up as 1 signal, okay? You've got a hydrogen atom here. That's going to show up as 1 signal. You've got a hydrogen atom here. That's going to show up as 1 signal. And let's see here if I'm running out of colors. There we go. You got 2 hydrogen atoms here. That's going to show up as 1 signal. And then you get the 3 hydrogen atoms here. I had to bust out the pencil for that one. So you're looking at, in this particular compound, you're going to see 1, 2, 3, 4, 5 signals in the proton NMR. Now, just having that information is really powerful, because if your compound, if you're thinking you're going to be making something very symmetrical, you're not going to be expecting to see a lot of signals in the NMR, but it gets better. So this is really just the tip of the iceberg. Now, just because we can count how many signals doesn't mean we know where they're going to show up. So the location of the signals is another really nice thing that NMR allows us to do. So it turns out that the location of the signals is pretty much based on chemical environment. It's based on chemical environment. And what I'm talking about there in particular is hybridization of the carbon atom that the hydrogen atom is attached to, and electronegative elements. Okay, so this can be a very powerful tool for, you know, trying to figure out which signals are associated with which hydrogens on the compound. So a typical NMR setup for a proton NMR usually is in this scale from about 0 to 10, and this is measured in something that's called parts per million. And essentially what that's doing is it's comparing the magnetic field that was needed to cause the NMR effect in a hydrogen versus the overall strength of the magnet, okay? And so that makes the numbers, you know, relatively easy to work with. Now, one peak that you're always going to see in every proton NMR is going to be the one down here at 0, and this is kind of your standard, your internal standard that the machine is. And that particular compound is a heavily shielded molecule. In other words, it is a very electron-rich system. And so this takes the machine quite a bit of energy to cause those hydrogens to exhibit the NMR effect. And so we use that kind of as our standard. This is referred to as tetramethylsilane, or TMS. So you'll see this in pretty much all your proton NMR spectrum. So it's not your sample. Now, as far as regions that you're going to find your compounds, so some terminology you should be comfortable with is, as you go further towards TMS, you go this direction, we call that upfield, okay? And upfield are more shielded hydrogens, hydrogens that are on carbons that have a lot of electron density. There's not a lot of electronegative elements pulling away that electron density, and the hybridization tends to be sp3, okay? If you go the other direction, this way, this is referred to as downfield. Downfield is less shielded, means it takes less of the energy to cause those hydrogens to interact. And so those hydrogens typically are on carbons that are sp2, sp hybridized, and are on carbons that are bonded to electronegative elements or close to electronegative elements. So this is another way to kind of delineate where the signals are. Now, to just kind of give you a hard and fast rule, and again, there's always exceptions, but you see I've kind of marked some areas here. So typically in the region from about 0 to 4, this is where you're going to find your typical sp3 bond to carbon with hydrogen, okay? And if the carbon is attached to an electronegative element, well, then it'll be further down towards 4, and if it isn't, it's going to be further up towards 0, okay? And it turns out that the more substituted that the carbon atom is, okay, well, that causes also the signal to shift downfield a little bit. So if the carbons are, you know, tertiary versus secondary versus primary, well, you can kind of see some differentiation in there, in that, you know, tertiary is a little bit further downfield than secondary, than primary, etc. But generally, these are all found in this region. Now, usually between 4 and 10, this is where you're going to see your sp2 carbon hydrogen and your sp carbon hydrogen signals. Sp, surprisingly, is not quite as far downfield as, as sp2, and that's because of how the pi bonds interact with the magnetic field, and there's a pretty good explanation of this in the PowerPoint that I'll kind of refer you to look that up. But this is where you find these signals. Now, right around 7 is where you usually see your aromatic, okay, signals. Let's say, so for your benzenes bonded to hydrogen, those are usually in this region around 7. And then all the way down here, usually between 9 and 10 in this region, is where you see your aldehyde. So where you have a carbon bonded to a hydrogen that's double bonded to an oxygen. And the only thing that's usually any further downfield than that is a carboxylic acid hydrogen, which is going to be one of your most de-shielded signals. Now, the other thing I'll mention about what the peaks look like, I guess we'll talk about this later, but the peaks have a different shape based on obviously which atoms they are attached to, and I'll kind of get into that in just a minute. But this is some of the general regions that you would expect to find your signals. Okay, so if we had to kind of do a guess a little bit as to where you would find some signals. Let's just say we had this compound. So this is known as paraxylene. So you have a 1,4-dimethyl benzene compound. Okay, so we'll start off. How many signals do you think you would see in the proton NMR? So obviously there's a plane of symmetry here. Okay, so these two methyl groups right here are going to show up as one signal. Okay. And then you've got your hydrogen atoms here and here and over here, because there's also a plane of symmetry that goes this way too. So all 4 of those hydrogens the machine treats as equivalent. So you're going to see 2 signals, okay? So the CH3 signal, okay, that's going to be probably in this region somewhere, probably around 2 to 3-ish, and that's because it's bonded to a benzene ring, so that pi bonds also kind of will cause signals to be shifted downfield a little bit as well. So if I had to guess, I would suspect that the signal right here for these 6 hydrogens, that this is going to be probably in the range of about 3, 3.1, something like that. And then these hydrogens right here, all of these then this one, this one, this one, and this one, those are all equivalent. And the way we typically do that in chemistry is we'll say, okay, these are your A hydrogens and all of these are B, so they're all equivalent. So all of those hydrogens are all going to show up probably around 7. And this symbol delta is the symbol to represent the parts per million on the machine. Okay. All right, so this is the second thing that you can get out of NMR is knowing where those signals are going to come. Okay, but there's even more. So the other thing is that the signals are not just always single peaks. It turns out that the peaks often are split. Okay, and when you see a splitting occurring, that is whenever a hydrogen atom is within 3 sigma bonds of another hydrogen atom, okay, that is non-equivalent to it, that will cause the signal to split, okay? So that means that if there are no hydrogens that are within 3 sigma bonds away from a hydrogen, that's all the hydrogens that are not equivalent, well, then there's no splitting, and that peak is described as a singlet. If there's one hydrogen, okay, that's within 3 sigma bond lengths away, well, then that's referred to as a doublet. You'll see a split in the signal. If there's 2, well, then that will show up as a triplet. And if there is 3, then that signal will show up as a quartet. Okay, in other words, you'll see a peak of 4. And so just to kind of give you an example of what those look like, a singlet's going to look like this, a doublet's going to look like this, triplet is going to look like this, and a quartet is going to look like this. Now, the reason why they're not all looking equal in size is it has to do with the spin that's associated with those electrons. And again, it deals with Pascal's triangle, and there's a nice explanation about that in the PowerPoint. But here, I'm just going to tell you kind of what the general shapes look like. Now, anything beyond this, you can have things called quintets and hexets and septets, but those start to look really messy. And so once you get a whole lot of splitting going on, well, we often just refer to those peaks as multiplets, meaning there's just a whole lot of splitting that's going on there. Okay. Now, if we had to think about this a little bit, and we had to predict some splitting patterns. Okay, so if we were to look at, let's say, well, let's go back to example we looked at earlier. Okay, so this was propane. Propane, we predicted that we would see 2 signals. Okay, and then both of those signals are going to be upfield from 4, probably closer to 0, between 1 and 0, because there's no electronegative elements here, no pi bonds. But what is it going to look like? Well, it turns out that, since all of these hydrogens here are equivalent, okay, they're not going to be split by each other. But if I draw it out a little bit, I'm going to draw these guys out. Okay, well, these hydrogens are 1, 2, 3 of them. And again, it's the same thing over here for this set too. They are 1, 2, 3 bond lengths away from this hydrogen and 1, 2, 3 bond lengths away from this hydrogen. So all of these hydrogens right here in this signal will show up as a triplet, okay, in the NMR, okay? These hydrogens, on the other hand, they are within 1, 2, 3 bond lengths away of this one, and of this one. And again, you want to be thinking plane of symmetry here. So again, it would be the same thing on this side. So these are effectively being split by these 3, okay? And so that's going to show up as a quartet. Okay. So you're going to have 1 triplet and you're going to have 1 quartet. And if you had to predict where they're going to be, since the triplet's only bonded to 1 carbon and the The quartet's bonded to 2. The triplet should be upfield, and the quartet should be a little bit further downfield. Now, to exactly where, well, that's not really important. It's probably going to be somewhere between 0 and 1. Okay. Now, if we were to try this out again, and we wanted to predict some splitting patterns, say we had this compound here. Okay, so there are 3 sets of hydrogens, okay, and so we're going to see 3 signals here, as I've color-coded them in. Okay, so the ones here in black, so these guys right here, these are going to show up as a 1, 2, 3, 1, 2, 3. They're going to be split by those 2, okay, and so this whole signal is going to show up as a triplet. Then this guy right here is 1, 2, 3. Okay, so it'll be split by this guy. And then 1, 2, 3, 1, 2, 3, 1, 2, 3. It's going to be split by that. Now, since both of those hydrogens are different, okay, sets of hydrogens, what you in fact do is you end up multiplying, okay? You end up multiplying the signal, okay? So it ends up being a doublet times in this case what would be a quartet. So would it be a doublet of quartets or a quartet of doublets? In any case, it's going to be pretty messy. And so this guy right here, this is going to show up essentially as a multiplet. Okay. And then the hydrogen here on the end is 1, 2, 3, 1, 2, 3 bonds away from these 2 hydrogens. And so this hydrogen is going to show up as a triplet. Okay. So you're going to have a triplet, a multiplet, and another triplet. Now the way you're going to differentiate them is this hydrogen is going to be much further downfield than these. So I would expect this one to be probably close to about between 9 and 10 parts per million. This one is going to be a little bit further downfield than this signal because it's closer to the carbonyl. So maybe that set's going to be closer to about 3 parts per million, and this one's going to be closer to 1, okay? And so that just tells you really fast, just guessing what you think those signals are going to look like and about where they're going to be in the NMR, okay? All right, now the next thing to consider here is the integration, okay? Now, the integration gives the lowest whole number ratio, okay, of hydrogens in the compound. And you want to be thinking this is more like empirical formula, even though that's not really what it is. It's not necessarily the exact number of hydrogens in the compound. Okay, so the machine can't tell you exactly how many hydrogens are there. It can just tell you the ratio. And that's because the machine views, again, symmetrical signals as basically symmetrical atoms and symmetrical hydrogens as the same signal. So for instance, if you look at this guy right here, okay, there's going to be 2 signals here that you're going to observe. And both of those signals are going to be singlets because you're more than 3 sigma bond lengths away between the 2 sets of the hydrogens, namely these hydrogens and all these hydrogens. But your ratio of hydrogens here is going to be 9 and 9 as 18 hydrogens. And this one right here is going to be 2 hydrogens. Okay, so if you were to guess what that looked like in the NMR, proton NMR, I suspect that, this is not to scale, but I suspect everything is going to be between 0 and 1 here because, there's no electronegative elements. So this is a little bit more substituted than all of these hydrogen atoms out here on the methyl groups. So this signal is probably going to be a little bit further downfield, so you're going to see 2 singlets. Now you'll notice right away that the signal sizes are different, but you can't just look at this and guesstimate it. So the machine actually does it for you, and it'll do it'll do this little integration symbol, which is basically what means to add up in calculus. And so you'll see something like this, all right, but then you're going to see another one over here. Now, the machine will tell you basically that this is 1 to 9, okay? That's a 1 to 9 ratio. But even though the compound does not have 1 hydrogen and 9 hydrogens, it has 2 and 18, but the ratio is what it needs to be. So you can't just go by the integration. You often need to have additional information to go along with that compound, and that's why there are other techniques to help you determine exactly what the compound is. But nevertheless, that's a fairly useful tool to have, okay? All right, so now putting all of that together, okay, and that was a lot to take in. We're going to work a few examples of this, and then we're going to be talking about carbon and mass spec. So I'm going to stop the video here. I'm going to let you guys kind of review your notes, and then when I do the next one, then we will work those examples and we'll take it from there. Okay, hope everybody's doing okay, and I'll talk to you again soon. Bye-bye.